Howdy. I love that about Aggie Land, don't you? Anyway, welcome to the third lecture in our first year chemistry lecture series. My name is Dr. Wendy Kennicut. You might have seen me. My office is in the back of the 101, 102 help desk area. So I'm always the one trying to wind my way through. Anyway, I'm really pleased to introduce our speaker. He's a wonderful speaker, and he's my wonderful husband. You know, yeah. And so he's going to be talking about something very near and dear to his heart, the science of Antarctica. Both of us grew up in upstate New York, and he got his bachelor's degree in chemistry from a little college, Union College, in upstate New York. He came down here to get his PhD in oceanography. He was studying the organic chemistry of the ocean, and he graduated in 1980, and we actually met in graduate school down here. And he then went to Tulsa. A big part of the organic chemistry in ocean water deals with the oil that naturally seeps up from the bottom of the Gulf of Mexico, and so he went to Tulsa to learn more about oil and run a lab there. Then he came back here and helped start an environmental chemistry lab, which ended up being called GERG, which is kind of an ugly name, but it stands for the Geochemical and Environmental Research Group here in part of the College of Geoscience. And he worked there for many years. He became director for 5 years. And now he's a full professor in oceanography, and he works in the vice president of research in that office now. Okay, and so how did all this Antarctica stuff come about? Well, back in 1990, there was an Argentine supply ship that ran aground right off the coast of one of the U.S. stations called Palmer Station. And because of this, there was an oil spill, and he led the group down to study the oil spill in Antarctica. And so they were monitoring this for a few years, and one of his bunkmates on his trip to Antarctica was the vice president, no, actually he was the president of UT Dallas. And he ended up getting involved in the politics of Antarctica, which is really interesting, and also doing studying in Antarctica. And so that's how all that came about. Anyway, so he's turned out to be studying in oceanography. He's turned out to be studying in Antarctica. He is now the vice president of SCAR, which is the Scientific Committee on Antarctic Research, that gives scientific information to the treaty which actually runs Antarctica. And so without further ado, I'd like to introduce my husband, Dr. Chuck Kennicut.
Thank you. There's always a little bit of danger with your wife introducing you. I was afraid you might start seeing my baby pictures up here on the screen. So she was pretty easy on me, and I do appreciate the opportunity to come here and speak to you tonight about one of my favorite topics, Antarctica. These are very exciting times for those of us that practice our science in the polar climates, and I hope to share a little bit of that excitement with you tonight. Nearly every day it seems, and I think you've probably seen it as well, that the polar regions are mentioned in the media for one reason or another. In fact, within just the last few weeks, there have been 2 episodes about global warming in the polar regions on CBS's 60 Minutes program, just to name a couple of the media types of attention that's been paid to the polar regions. As you've heard, this public lecture series is about how general chemistry applies to real-life situations. As the title of my talk infers, chemistry is at the very heart of much of the science that's conducted in Antarctica, and I'll share various aspects of that science with you tonight. When Eric and Wendy first asked me to provide a presentation on Antarctica, many topics came to mind. such as the ozone hole that I'm sure you're all familiar with, caused by chlorofluorohydrocarbon emissions, atmospheric transport of persistent organic pollutants that have resulted in the appearance of pesticides in the Antarctic food webs more than 40 years ago. This was recognized. And then one of my areas of interest is the general area of the impact of humans' presence in Antarctica, just to name a few. But as I thought about the talk, it struck me that a common element to some of the most exciting chemistry occurring in Antarctica was directly related to the critical role that water plays in polar processes. And so that is the common theme that I wanted to talk about tonight, and hopefully you'll recognize some of the principles you either have been taught or will be taught in first-year chemistry program. Water is the second most abundant molecule in the universe, only behind hydrogen. It seems like water is an appropriate topic today with all the rain that we've had. Water is the simplest compound of the two most reactive elements in the universe, which are oxygen and hydrogen. And even we are more than 2/3 water. And without it, we would die in just a few days. So water is a very important molecule. It acts as a structuring solvent, a solute, a reactant, and probably most importantly, a biomolecule. And we'll come back to each of these different roles that water plays. And in fact, life as we know it would not have evolved or continue to evolve without the presence of water, in particular liquid water. So as I mentioned, water is a very simple molecule consisting of two hydrogen atoms attached to an oxygen atom. However, it exhibits a very complex behavior and has very unique properties. Hopefully you'll recognize this if you've done your homework in first year chemistry. This is a phase diagram of water. And this is the simplified phase diagram for water that you probably have seen in the classroom. But in fact, the behavior of water is much more complex than this. And one of the take-home messages is that very simple physical processes can actually have very profound effects. And I'll go through a range of these effects that are directly related to science that's conducted in the southern regions of the Earth. Phase diagram, I'm sure as you know, shows the physical state of matter at different temperatures and pressures. Within each phase, the material is uniform in chemical composition and physical state. The lines on this diagram represent the boundaries between phases, and a change in temperature along these boundaries can cause the phases to abruptly change from one to the other. Where three lines join, this is what's called a triple point, where three phases can coexist. Critical point is where two of the phases become indistinguishable from each other. And as you can see, the phase diagram of water is very complex, having a number of triple points and possibly one or two critical points. Also on this diagram, you'll see the Roman numerals, and that is designating 11 different crystal structures for ice. And some of these, though, are only theoretical or only exist in the laboratory. But water occurs in very many different solid forms. This structure, the hexagonal ice, is actually the form of almost all natural snow and ice on Earth. And this is evidenced by the six-fold symmetry that you see in ice crystals and snowflakes. So what about water on Earth? As you know, we're known as the planet of water. In fact, water is quite common throughout the solar system and the universe, and I'll talk about that a little bit more. But 97% of Earth's water is in its oceans. However, there's only 3% of the water on Earth that's fresh water. And of that fresh water, though, 80% of the fresh water is contained in one place, in Antarctica. And just to set the context, I hope most of you have heard of Antarctica. It's engendered a lot of great public interest over the years due to the intrigue of a distant and cold land that often evokes images of adventure and danger. I'm sure most of you have heard of the heroic age of exploration with the likes of Scott and Amundsen's race to the South Pole. as well as the fairly unbelievable adventure of Ernest Shackleton and the Endurance. But what I've heard and seen over the years of giving Antarctic presentation is there's also a lot of misinformation. So I thought I'd just throw out some facts that you may or may not know. First, Antarctica is a continent. It's the 5th largest of the 7 continents on Earth. Its land mass is about 50% larger than the U.S., so it is a significant continental land mass. It's in the southernmost regions of our planet. I often hear people say Antarctica is up there. It's actually down there. It's in the south. It's south of South America, Australia, New Zealand, and South Africa. Antarctica is generally considered those oceans and land masses south of 60 degrees south latitude. And just to be clear, penguins do live in Antarctica in the south. Polar bears don't. Polar bears live in the north. There are indigenous people living in the north, and there are no indigenous people living in Antarctica. So anybody that's in Antarctica is a visitor. And as you can see from this, Antarctica is a continent surrounded by oceans, which is very different than the North Pole or the Arctic region, which is actually an ocean surrounded by continents. The Southern Ocean is interesting in and of itself. It accounts for more than 10% of the world's oceans. It's the origin of the dense cold waters that fill all other oceanic basins on Earth. This is where the conveyor belt you may have heard about that we believe is intricately linked to climate change begins due to the sinking of dense cold water to the bottom, which eventually migrates all the way north to the northern polar regions. Antarctica is covered by rivers of ice. This is a massive ice sheet that reaches more than 4 kilometers. And ice does flow just like rivers. It just flows at much slower velocities. And the middle of this slide shows you the actual ice sheet velocity. So the ice sheet is in constant motion. As I mentioned, Antarctica is the home to 90% of the world's frozen water and 80% of the world's fresh water. On the far left-hand corner, here you'll see a yearly, monthly extent of the sea ice. The other thing to notice is that Antarctica, as much of our planet, is always changing. In this particular case, over 20 million square kilometers of sea ice is frozen every year. And in the summer, 2/3 of this melts. So the turnover and the transformation from ice to water is an ongoing and continuous process that occurs particularly in the polar regions. One of the things you probably hear about in the news quite often is this calving of large icebergs from the ice shelves around Antarctica. In this case, it shows an iceberg the size of Long Island that has freed itself from the ice sheet and then is moving away from the continent. In addition, in recent years, there's been disintegration of some of the ice shelves around Antarctica. This shows the Larsen Ice Shelf in 2002. This is a satellite image of a large floating mass on the eastern side of the Antarctic Peninsula, just below South America. The ice shelf shattered and separated from the continent in 2002, forming a plume of thousands of icebergs. More than 3,000 square kilometers of shelf area disintegrated in just 35 days. So this was quite a dramatic event. And over the last 5 years, the shelf has lost a total of 5,700 square kilometers and is now only 40% of what it was just 5 years ago. So recent reports also suggest that the Antarctic ice sheets are retreating, though that's still a matter of controversy. But the, I guess, billion-dollar question is this global warming, and is this due to the greenhouse effect and related to human use of fossil fuels? Ice acts in many ways as the thermostat of the planet, and most ice, as I've already mentioned, is in the polar regions. Hopefully most of you have heard of the greenhouse effect. This is, again, an effect that's based in chemistry. The greenhouse effect is the rise in temperature that the Earth experiences because certain gases in the atmosphere trap energy from the sun. Without these gases, heat would escape back into space, and the Earth's average temperature would be about 60 degrees Fahrenheit colder than what it is today. We usually hear bad things about the greenhouse effect, but in fact, the greenhouse effect to a certain degree is a natural phenomena, and it helps to moderate climate, making the planet more habitable. There are a variety of greenhouse gases. You're probably most familiar with carbon dioxide, and you'll notice on each of these that they have a natural source as well as a anthropogenic or human source. Again, the combustion of fossil fuels has demonstrably raised the CO2 levels in the atmosphere, and I'll show you that data in a second. Methane is also a greenhouse gas that has both natural and human derived sources, nitrous oxide, and then there's a whole range of other gases. And on this slide, we show the infrared spectrum of each of these gases, and that's actually the wavelengths of the energy that's absorbed as part of the greenhouse effect. So this chemical mix of gases is really what the whole underlying debate about, and again, this is all based on chemistry. And of course, I think one thing that goes unrecognized is water vapor is actually the most abundant and the cause of most of the greenhouse effect, simply because there's so much water vapor in the environment. So what is the record of climate change, and how do we interpret that? Here I show some of the classic diagrams that present the evidence for global warming and climate change in our time. On the far right at the top was commonly called the Mahlon lower record, which is the record of CO2 over the past 50 years. And these are direct atmospheric measurements of CO2 by a scientist named Keeling. This is often called the Keeling CO2 curve as well. But it only covers about the past 50 years of our history. The next diagram down is one that gets a lot of conversation. This shows the rapid increase since the turn of the last century in not only CO2 levels, but also in the ambient temperatures worldwide. And then finally, the Vostok ice core. You may wonder, how do we get a picture of past climates? And I'll talk a little bit about that in the next slide. But there are ice cores that go back hundreds of thousands of years that contain a record of climate change. And that's really the basis for then predicting what we believe future changes in climate will ultimately play out. So these are records that are from actual measurements. They're also reconstructed from ice cores. And then the longer records, as I mentioned, go back quite a ways. In fact, recently over nearly 1 million year old ice has been recovered in the thickest part of the East Antarctic ice sheet. But going along with the theme of this presentation, this is actually a record of chemical change. And all of these interpretations are based on various chemical measurements. If you wonder what is the foundations for making these claims about climate change and what the cause of recent global warming is due to. And it's everywhere from the isotopic measurements of water, what happens with increasing pressure from snow deposition, snow becomes compacted and air is trapped within the deposited layer. And so we have these time capsules of ancient atmospheres that are captured in these ice cores. And so the composition of the bubbles of air is a measure of the composition of atmospheres in the past. Of particular interest is obviously the ambient temperature of the atmosphere. And this is directly measured from looking at the stable isotopic composition of water. And in particular, the ratio of the heavy isotope O18 relative to the lighter isotope O16. Along with this, they also use measurements of deuterium and hydrogen to indicate the temperatures of past environments. During cold periods, the concentration of less volatile isotopes in the ice is lower than during warm periods. And you can see in the far right, this is a calibration curve that actually provides a direct translation of stable isotopic composition water into what the ambient temperatures were. The central diagram shows the close correlation between the CO2 in the ice bubbles and the changes in temperature that have been derived from the stable isotopes. And again, this is a chemical measurement. It's based on gas chromatography and either thermal conductivity or other detectors quantifying the amount of gas that's present in these trapped air bubbles. To date these cores, radiogenic dating is used. And again, this is a chemical method using isotopes, radiogenic isotopes such as carbon-14 and chloride-36. And then finally, the dust and the salt that's in these ice core records is also analyzed, in this case for the major anions and cations, by ion chromatography and elemental analysis. So again, I hope you see the connection between the chemistry, which is really the record of climate change, and how the principles that you are learning in the first year program directly apply to questions that are really part of the common debate now worldwide. So building on that, how does ice balance against global warming? And what I thought I'd demonstrate here is just on basic general chemistry principles. You could do this calculation yourself, just using some facts about our planet and concepts that you're learning in the first year program. First of all, ice melting is endothermic, so melting of ice will offset a rise in ocean temperature. One of the complicating factors in understanding climate change is most of what you hear about is atmospheric temperatures, when in fact the long-term repository of temperature on the planet are the oceans. So the transfer of heat to the ocean is more difficult to quantify, but the latent heat built up in the ocean will take decades, if not centuries, to ventilate. So if we continue to heat the ocean through increases in air temperature, even if we stop CO2 emissions today, the final impact will play out for years, if not decades or centuries to come. So looking at the question, how much ice would be melted to counteract just a 1 degree C rise in ocean temperature? The general chemistry principles of heat of fusion and of ice, the specific heat of water, can be used to solve for the unknown, which is how much ice would be melted, given that we know the mass of the oceans on our planet. And the calculation comes out that 1 times 10 to the 22nd grams of ice would be melted in order to counteract just 1 degree C rise in overall ocean temperature. What this means, since we at least roughly know the mass of ice in Antarctica, is that about 50% of the ice in Antarctica would melt in order to counteract a 1 degree C rise in the ocean. So if, in doing other calculations, this melting of 50% of the ice just on volume would raise sea levels by 40 meters, or almost 120 feet. So if the entire ice sheets on Antarctica melted, sea level would rise upwards of 80 meters. And you can see here, College Station is only at 97 meters, so it should give you some indication. Now, what's the likelihood that all of the ice in the Antarctica is going to melt? In your lifetime, probably 0, but on various time frames, this type of change in the mass of Antarctic ice has occurred not only once, but many, many times. And so I wanted to go back in history a little bit, the geologic history of our planet, and describe how some of these changes, and obviously these changes have happened before people were intervening in natural systems and burning fossil fuels. So these are natural changes that have occurred. In this case, this is a reconstruction of what the Antarctic ice cover looked like 20,000 years ago during the last glacial maximum, in other words, the last ice age. And you can see here that the current repository of ice in Antarctica is substantially reduced from what it was at the height of the last glacial period. Ice sheets evolve over time. This diagram shows the slow evolution of the ice sheet in Antarctica. Looking even further back, this is about 45 million years ago when this trend began. As we see today, glaciation begins at topographic highs, much as glaciers today occur on mountaintops. And then slowly as the region cools, these ice sheets grow, move down the mountains, and ultimately covered all of Antarctica. But you'll notice that this took several millions of years for this to occur. What's interesting, though, is that we may be witnessing the reverse of this trend with the retreat of glaciers worldwide. I'm sure most of you heard the snows of Kilimanjaro are actually almost gone, and this is being repeated in mountain glaciers all over the globe. But the difference here is how rapid this change is happening. In the past, as you can see here, this took millions of years, and now things seem to be changing in the order of centuries, and in some cases they're evidence of major changes even on the time scale of decades. And you may have heard of the phenomena of abrupt climate change, where we really don't understand, but the climate could go into a new state by triggering events that are really not well defined. So that's really what I think is driving a lot of the concern. This graph on the right, if you notice, the bottom part of the scale is 45 million years. The top part of the scale is only 500 years. So there's quite a bit of difference in the speed at which the changes are occurring on the planet today. That doesn't necessarily infer that it's all human-induced, but it certainly does raise the question of what will the changes be in the next 50 to 100 or even 500 years. Well, looking even further back, a number of scientists now theorize that at one time in the Earth's history, it actually was completely entombed in ice. And this is what's commonly referred to as the snowball Earth. And this is nearly 600 million years ago, 600 to 700 million years ago, when it's believed that due to changes in the planet itself, that ice became the predominant form of water across the globe, not just in the polar regions. And some scientists believe these episodes have happened 3 or 4 times during the history of the planet. One of the intriguing questions, though, in the graph on the left here shows the timing of the snowball Earth that's hypothesized and the advent of various types of organisms on Earth. And you'll see that they coincide. So one of the questions is, how did organisms manage to go across this physical barrier? And this will, believe it or not, we are coming back to Antarctica. It turns out that Antarctica has certain environments that are very similar to what might have existed during the snowball Earth. And I think most of you know, again, the chemistry of life is one that's very well studied. Here, life in the light, where your energy is derived from photosynthesis. Again, you see the primary role that water plays in the reaction with CO2 to produce organic matter. And again, pigments are any substance that absorb light. This is an example, chlorophyll. And the color of the pigment, though, comes from the wavelengths of light reflected. In other words, those not absorbed. So chlorophyll, which is a green pigment, absorbs all wavelengths of visible light except green. And these photosynthetic pigments are the ones that provide the mechanism for electron transfer to be able to synthesize the organic matter that's needed to build cells and for an organism to exist. In each of these steps is a coupled oxidation-reduction reaction. And often water is oxidized as a result of this photosynthetic activity. Now, different to this is life in the dark. In this case, it's called chemosynthesis rather than photosynthesis. And chemosynthesis provides an alternative to photosynthesis in environments that are isolated from light. The most famous cases are the tube worms at the hydrothermal vents or the hot vents. Also the communities detected right here in the Gulf of Mexico by our group at the Geochemical Environmental Research Group that are now called cold seeps, where organisms exist primarily on oil and gas seeps below the photic zone. And then also there's bacteria that occur at mineral surfaces themselves. In this case, the picture shows bacteria growing on pyrite crystals. Some believe that chemosynthesis, in fact, is one of the original strategies that allowed for life to evolve on Earth. And so this may be a mechanism that allowed organisms to actually flourish even under harsh conditions. Excuse me. Here we have the phase diagram again, only now it's looking at where can life exist. In fact, life lives within an envelope of various conditions. Here looking at temperature and pressure. Bringing us back to Antarctica, I'll talk about two specific sites that are being studied, the dry valleys, and then also Lake Vostok, one of the subglacial lakes. But life exists within this envelope of factors that may be limiting, and temperature and pressure are two of them, but also, as I mentioned, light limitation, and also there are other factors such as nutrient levels. And scientists study life in these extreme environments, life on the edge, to provide clues about where we might expect to find life beyond our planet. And I'll give you some examples of that toward the end of this presentation. But as I mentioned, there are already two such places that start to approach these envelopes of where life can live, and this is the dry valleys in Antarctica. The McMurdo Dry Valleys here just shows you some pictures of these locations. They're actually the driest and coldest ecosystems known on our planet. These microbial communities are exposed to constant low temperatures. In many cases, the ecosystems are isolated and permanently frozen lakes so that they're decoupled from the sun. And as I just showed you, oftentimes chemosynthesis is the basis of life. And also there's some very unique physiologies and diversity, but studying these organisms give us clues to what are the limits to life and what types of environments might be elsewhere in the solar system that would support life. The next thing I wanted to talk about is subglacial environments underneath the thick East Antarctic ice sheet. Because of the right temperature and pressure, you actually can have liquid water. One of the more famous locations is Lake Vostok, which is here. And that's a very large feature. I'll show you a satellite fly-in to Lake Vostok. But these are exciting new frontiers for exploration and exist under vast ice sheets when there's more than 2 kilometers of ice above to provide the right pressure in order for liquid water to occur. This is a NASA fly-in to Lake Vostok, and you can see that you actually can see this from space. This is a large feature. The length of the lake is almost 300 kilometers. It's similar in size to Lake Ontario. And even though it's below 4 kilometers of ice, the surface of the ice shows these flat features that very much are lake-like. So the question is what types of life might live in these very unique environments? Tying back into some of the things that we discussed before, it just turns out from serendipity that Lake Vostok, the largest of the subglacial lakes in Antarctica, in fact the largest known on the planet, is right below Vostok Station, and this in fact is the Vostok ice core that gives the 400,000 years of climate history. Underneath this, again, because of the temperature and pressure conditions and the geothermal heat that comes from deep in the subsurface, liquid water occurs even at these great depths. In this case, there's parts of Lake Vostok that are more than 1,000 meters deep. We also know now that there are sediments in the bottom of these lakes, and they're a target of exploration over the next, I'd say, 5 to 10 or more years. And so the whole question, these have never been penetrated before, so this is an entirely new area of study that really has just gotten started in the last 5 to 10 years. The Russians are very close to penetrating the lake. They deepened the hole just this last season and expect to enter Lake Vostok within the next 2 years. Too many clickers. Up until this point, the study of these environments has been remote by geophysical techniques, but also ice has been recovered from the Vostok borehole. An interesting phenomena is that, in fact, because of the differential in pressure between one side of the lake and another, that ice freezes on the bottom of the ice sheet and is transported out of the lake, while on the other side of the lake, the ice actually melts. The Vostok borehole is penetrated in what this is called the accreted lake ice, so we know that this is actually ice that's been refrozen from the lake, and it's the only samples that are currently available for study. Of interest here, because of these very slow and unique conditions that this ice is forming, there are ice crystals here that are 6 to 8 feet in length, so it's very unusual ice. And again, virtually everywhere that scientists have looked on Earth, we ultimately detect life. But exactly what's in the lake still remains unknown. This type of study takes a lot of technology. It's not only do you have to drill through 4 kilometers of ice, enter the lake, do various types of sampling, which could be introducing various types of probes, also observatories or autonomous vehicles, but then also you have to be able to put it down a borehole that's very small. So this requires a lot of technological ingenuity to be able to do this and do it in a way that doesn't alter these unique environments. And one of the interesting things is that NASA has been very interested in these locations to develop techniques for planetary exploration beyond Earth. And so, coming to the end of my presentation, I wanted to come back to this, talking about water, but now in the broader picture, water in the solar system. We've talked specifically about Antarctica and the types of environments that are there that give us clues to where life may exist beyond our own planet. On this slide, this is the average conditions on Earth, this is the average conditions on Mars, and the average conditions on Venus. So we can see that, again, Earth is in this unique position, at least on average, right at the boundary between solid and liquid water. Now, one of the things that we know is that liquid water is key to life, and so that's why there's always so much excitement when NASA detects water on one or more bodies within our solar system. I guess one of the ultimate questions, are we alone, is what drives a lot of this curiosity. Europa, the icy moon of Jupiter, appears to have a liquid lake beneath an ice crust that looks very similar to what we might suspect the East Antarctic ice sheets look like. And so this is a target of exploration to detect life beyond Earth. And I'm sure you've heard a lot about the discussion of detection of water on Mars. This is a polar, in the polar region, showing water actually frozen at the surface. And now there's belief that, particularly in the past, that Mars had substantial oceans and abundant water. And the question is, how or if did life evolve on Mars? And just real recently, in the press, maybe you've seen this. This is a moon of Saturn. It's called Enceladus, and it turns out recently on a flyby, they saw these plumes that appear to be geysers of liquid water. So once again, the crust here, though, as far as I understand, is a methane hydrate, or just a methane frozen crust, but beneath it, they believe again that there are actual liquid waters. So this is another example, and it appears the more we looked, the more we find water throughout the solar system. But the real question is there liquid water, and are the conditions right to be able for life to live in these unique conditions? And again, going back to Antarctica, studies in places like the dry valleys and subglacial lakes will give us clues to that. Next thing I wanted to talk to you about was hopefully you've heard some things tonight that have piqued your interest. It turns out that the International Polar Year will be starting in a little bit over 12 months. In fact, maybe less than 12 months now, March of 2007. And this is a major international effort to really put a focus on the polar regions and work on some of the problems that I've outlined. The International Polar Year has a history of being conducted all the way back to the 1880s, the first polar year. Then in the 1930s, there was a second polar year. And then in the late 1950s, the International Geophysical Year. And the International Geophysical Year was a very significant time for global science. And as you can see, the number of nations have been increasing over the years. And at least the last I looked, there were over 40 nations participating next year in this the fourth International Polar Year. As I mentioned, the International Geophysical Year, which some of your parents may remember, was really quite spectacular. It was the beginning of space science. Sputnik was launched. Explorer 1. It was the first time they realized that the Antarctic ice sheets were several kilometers thick. It was the original discovery of the ozone layer in the ionosphere. And so there were just major advances in the Earth sciences during the International Geophysical Year. And we hope during this next International Polar Year that the same type of legacy will be created. And I'll just read this. This is what it's described as an international program of coordinated research to explore polar regions, deepen our understanding of polar interactions, including their role in global climate, expand our ability to detect change, and extend this knowledge to the public and decision makers. And so there'll be a major public outreach and education portion of the Polar Year. And I certainly would encourage you to follow this as it develops. So I wanted to end my remarks with a quote and an invitation. I guess I forgot the one in the beginning. Leonardo da Vinci said that water drives nature. Paraphrasing Lauren Isley, a philosopher and writer, if there is magic on the planet, and I'd say, or in the universe, it's in the water. And hopefully you've seen a glimpse of that tonight. And then, as I mentioned, I want to invite you to join us for the International Polar Year and participate in the excitement of Antarctic chemistry and science. Thank you. So that there were dancing penguins.